you and welcome to everyone for joining us tonight for AFI Victoria's very first webcast presentation. We appreciate each of you taking your time out of your evening or afternoon, depending on where you're joining us from, to attend tonight. Tonight's presentation will be co-presented by Gary Savage from CSIRO and Adam Hassel from HASCO Foundry. For those of you who don't know both or either of them, I'll give you a brief background on each so that you can understand. Adam was born and raised into a family of foundry pedigree. At uni, Adam studied systems engineering and applied computer science at RMIT. Upon leaving uni, Adam worked at an engineering firm in Ballarat that developed simulations for the military, developing modelling software. In 2012, Adam rejoined his family business. Late 2013, HASCO was approached by the owners of Grisby's Foundry, also located in Ballarat, who indicated that they would like to try something new and proposed HASCO merge with Grisby's. In March 2014, the merge was complete and they had operated at the Grisby's site in Ballarat ever since. Adam and HASCO have often taken advantage of 3D printing technology, with the Foundry being the first commercial use at CSIRO. Gary Savage. Gary is CSIRO's principal research scientist located in Clayton, Melbourne, and leads activities on the 3D sand printer in Lab 22. Gary completed a metallurgy degree while working as a trainee at the BHP Whyalla Steelworks, and since has worked at Hawker de Havilland and BHP Research. Casting has been part of Gary's working life for over 35 years. Tonight, Gary and Adam are going to highlight two case studies where 3D printing has replaced conventional moulding and methods for production volumes in Australia and also in Germany. We hope you find the presentation informative. I now hand you over to Gary.
Thank you, Amber. A great introduction. Yes, this is where 3D printing is replacing conventional moulding. Two case studies, Australia at HASCO and one in Germany. I'm now going to put up the presentation. Hopefully you will soon see the PowerPoint slides. What we talk about a lot in Lab 22 is that complexity comes for free. It's a bit of a catchphrase. It's basically true, but in most manufacturing processes, and particularly in your foundry when you're talking about patterns and molds, complexity does not come for free. Once you get really complex cores, really complex molds, suddenly your pattern costs are going up. So complexity comes at a cost. So a benefit with 3D printing is when you've got complex things. Now, the examples I'm going to talk about are an impeller core and a water jacket core. Let's start with a bit of sort of 3D sand printing 101. This is important because I want you to understand the technology and what goes into producing a part 3D printing sand. So what you're looking at here in the video is the 3D printer working. At the moment, that's the print head indexing across the bed of sand, printing binder onto the acid activated sand. So in additive manufacturing terms, it's a powder bed inkjet binder type of machine. The powder is silica sand, the binder is a furane based binder. What's happening now is the recoater is laying down the next layer of sand. In between the print and the recoater, the Z-axis went down 0.3 millimeters. So each layer is 0.3 millimeters thick. Keep in mind the print area that we can print is 1060 by 600 by 500 millimeters. It can print about 22 millimeters per hour in the Z-axis. So a full box takes about 22 hours. It's a nice number because when you're doing production, you can finish a job and load the next job all within a 24-hour cycle. Nice and handy. So I hope that's clear. I'm now going to move on and explain other parts of getting something printed. Call it pre-processing. If you want anything printed on a 3D printer, you've got to start with 3D CAD geometry. A lot of people, and I even see it with students from universities and around, a lot of people haven't got the ability. There are people out there that can help you. So also people come to me and they say, oh, can you print this part? And I said, well, that's a geometry of a part. I need the geometry of a mold. You guys understand this. Some people don't. Anyway, you give me the CAD. This is the CAD of a impeller core. And it's actually the core that we're going to talk about later with the Hasco example. So you've got to place these things in the job box and place them in a way that you best utilize the space. Just going to run through a little animation. So you could copy the part, flip it around, that's the thing in green, and bring it up close to the other one so they don't touch. You can then duplicate those two and group them together, and that'll give you the basic building block to fill up the job box. So now what I'm going to show is that that basic building cell you can build in a matrix. So I want 2 of them in the x-axis, the long one, and I want 9 in the z, and I want about 1 millimeter between them. You just hit OK, and it fills the box up. They're blue because they're outside the print area. This is not good. So you can just select them and center the whole lot. Green is good. So that way I can work out, if you sent me a file, a rough costing, or if you've sent me a file, this is what's got to be done before you begin printing. It can be done fairly quickly. And once you get the hang of this and you do more and more printing, you can actually do this layout yourself if you know the dimensions. 1060 by 600 by 500. Put it in your CAD model, make things fit, make sure the individual parts don't touch each other. All right, next, when you finish the printing, there's a few things you've got to do. This is showing the removal of the job box. So you get an idea of the box, how big it is. So contained in that box is the full sand print. And remember when it was printing, you see an area where the binder was printed. So wherever the binder was printed, that's going to go hard. Anywhere else is just loose sand. You then move over and you slide the job box into what's called the unpacking station or unpacker. Once it's in the unpacker, the floor can be pushed up to reveal the job. So on your top left, it's showing the unpacking operation. So you can see the loose sand and then all the individual printed parts. This is a V8 intake manifold. So it's a bit like an archaeological dig. You want to know where the parts are and you've got to safely remove them. This job, it's actually, the mold is printed, assembled, but with gaps between them. So it takes time to remove them. You've got to brush the sand off and then you take it across to what's called a finishing station and you can blow it with compressed air to do the final cleaning. Then you've got to, like the image on the bottom right, you could assemble the mold components and the cores and ship it that way. Or in that image on the bottom right, you'll see on the pallet a whole lot of thin cores. How are you going to pack those? They're a bit delicate. So that's a bit of an issue. And it's an important point when we talk about impeller cores. because they can be quite fragile. So the cleaning and the packing is a substantial part of the printing process. Also, when you're finished, you've got to clean up, particularly the printer. The top left is an image of where the job box was, but you can see the white sand still on the machine bed. That's got to be cleaned. The recoder's got to be cleaned. Lots of cleaning to be done. Waste has got to be taken away, etc., etc. Now I want to move on to giving you an idea of what the cost is. First question I get is, what's it going to cost me to make my favorite little thing? Whatever. So I try to be open with people, and I'm giving you all the figures here. So number one, the printing cost. That's basically the time that you're using the machine, $70 an hour. And I define that as the time that you're using the printing part of the machine so that another part can't be printed. So it takes about 22 hours for a full job box, or if you're not printing the full depth and you know that your thing is 110 mil high, that's 5 hours because it's 22 millimeters per hour. You've got to include 1 hour for cleaning and also the pre-setup of putting the layout in the job box. Now the consumables. There's silica sand, there's activator, there's binder, and there's ethanol, which is on a cleaner roller. Don't worry about it. But you add all of those together, and the cost is $2 per kilogram of printed sand. So when you've got your CAD and you know what you're printing, work out the volume, use a density of 1.6, and you'll get a weight. And that'll tell you how much your consumable cost is. Next comes the kicker. If you're getting CSIRO to do this job, our charge out rate is $250 per hour. I wish they'd pay me $250 an hour. They don't. But that's what I've got to charge you. There are other options I'll go into a little bit later. So what's the labor component? I've got to put the CAD, lay it out in the job box. I've got to clean the machine. I've got to unpack that job box, clean all the parts, and then I've got to repack them for transportation. So labor can be a big part. Let's take an example. Let's just take this. These are fictitious numbers, all right? It's a full job box. Let's say you've got 4 basic parts in there. It fills up the job box. Your print time in blue makes up about 50% of the cost. It's $800 per part. So it's about $3,000 for a full job box. That's the way you can guess how much it's going to cost you if you get us to do it. Look at the labor component. I'm having trouble reading at this distance. About 1/3. All right. What if you had 100 parts in the box? So now it's only $40 per part. But 100, that makes $4,000. How come it's more? Because the labor component has gone up. Because I've got to handle 100 parts, dig them out of the archaeological dig, brush them clean, blow them dry, and then I've got to find some way to pack them in a box and ship it off to you. So labor is a big part, even though the per part cost has gone down. Now, I did say there's another way of doing it. You don't necessarily have to use CSIRO labor. And maybe I'll touch on this at another time, but there are people who have been trained in the operation of the VoxelJet machine, and they can basically hire it. They just call me up and say, can I have the machine tomorrow? I say, fine. So they get charged $70 an hour for the printer, $2 a kilogram for the consumables, and then whatever their labor rate is what they put on the cost of making it. If you're interested to know who can do that, contact me. My details are at the end of the presentation. Let's move on to Hasco's case study. Adam contacted me and said, I'm looking at the possibility of doing this core. It looks something like this. He mocked up a really quick CAD, and you can see that in the bottom right. And he said the dimensions are basically right, the details are not there yet. So I played around and I said, look, I can get 96 of them in a box. So the ballpark cost would be blah. Okay. Let's go into the actual case. So this is the final drawing of the impeller core that Hasco is using. I gave him two prices, one with 96 in the job box and another one with 72 in the job box. The one with 72 was about 30% cheaper. So how do we do that? You would think 96 would be cheaper because you're dividing the cost over 96 instead of 72. Well, remember I said labor is a big part and so is packaging. So basically what we did is we eliminated my labor for the unpacking and cleaning and simplified the packaging. Let's have a look at how it's done. So here were the 72 cores laid out in the job box. Basically what we did is then just printed a box around them. The box has got to be thick enough to hold the loads during transport and sliding off from the unpacker, all of those sorts of things. So the base is fairly thick, side walls are thicker, but the lid, which you can see a hole there, is very thin. It's only 4 millimeters thick. So I didn't have to do any unpacking. They're printed like that, slide it off, put on a pallet and sent away. Here's another bit. Adam said to me, oh, I got these strainer cores, and can you fit any of them in the gaps? So I could fit 24 of them in the gaps. So basically, those strainer cores are printed for next to nothing because the cost has already been costed in for all the printing and stuff like that. There's only an additional cost of the consumables to print them, which is about 70 cents each. Let's go over this. So if I had 72 in the job box, so now my labor is only 11% because I've printed everything in the packaging in the box. So that's how it can change the cost. I hope that's clear. I haven't stated any numbers and costs for obvious reasons. I think you all know them. So let's give a few sort of holiday snaps of the process of making these cores. So what you're seeing here is one layer during the process of printing the impeller cores in their own box. So you can see the impeller cores, some are inverted, some are not, and you can see the boxes around them. When that job box is removed and the floor of in the unpacker is pushed up, the unbound sand just falls away until you get all the way up, and then just give it a quick brush on the outside, slide it off onto a forklift holding a pallet, put a bit of Glad wrap around it to stop it moving, put a couple of simple blocks on the side to stop it moving, and then Glad wrap it a bit more and put fragile, and I hope that the forklift driver doesn't drive into the side of it. And that's how it was shipped to Hasco Foundry in Ballarat. When it got there, all they had to do was, like I said, crack the egg open, which is the top. It's only 4 mil thick. Peel it away. You can see some of the pieces in the top right of that picture. And then they do the unpacking and the cleaning. Because for me to ship those cores, if I did the unpacking and the cleaning, I would have had to pack them back in sand, some way, in a box and ship it to them. And then they'd take it out and they'd have to clean it again anyway. This is double handling. So we just got rid of all that. So the foundry takes them out of the unbound sand, blows them, cleans them up, puts them straight in the mold and cast. Adam might tell you a little bit different. He might bake them to make sure they're dry before he puts them in the mold. What I'm going to do now is hand over to Adam, who's going to walk you through his side of the story. Just hang on while I stop sharing, and I'll now hand over to Adam.
Thank you, Gary, for the intro. I trust everyone can hear me. I'm sure Gary will join back in and tell me if he can't. I'll get straight into it. This is the casting that we're trying to make. It's an impeller. It's a bronze impeller, and it's a sand casting. It's made using two halves of a mold. So there's a bottom half of the mold, the top half of the mold, and then there's a third part, which we call the core, that chunk of sand that basically forms the hole in the middle, and that's the core that we've been talking about. So probably the best way to help justify the process of using 3D printing instead is to show you how they used to be made. And when you see how tedious and painful it is, you'll get an appreciation as to why we're trying to find an alternative method. So what I'll do is I'll just swap my video over so I can show you. Bear with me a sec. Okay, and we're back. So the original core, that's it there. That was made the old-fashioned way using a core box. This is the core box here. So as you can see, there's lots of little inserts here. These inserts are what form the vanes inside the impeller. And for strength, we have to insert all these little core irons. So Paul's just going to go ahead and pop them in now. I'll get out of the shadow of the light. So these are like making concrete. When you cast concrete, you want to put Rio in there so that you've got extra strength. And in this case, the concrete is the sand, and these, what we call core irons, are going in to give strength to the core. So we have to put a core iron in between each vane. So this is a fairly tedious process. Bear in mind that before we've even started doing this, we've actually got to spend quite a bit of time finding the core irons, getting a hammer out, hammering them all flat, bending them to the right shape, making sure they're going to fit. So once you've got to that stage, you have to mix your sand, you have to put the sand in, you have to get the sand to be probably 5 to 6 mil thick, then you have to put the core irons in, and then you have to fill it up with sand, and then to get the dimple, see how there's a dimple inside there, that's what comes from that tooling. So you now have to put that on the top, give it a shake, and you have to strickle the loose sand away from here, which is important because we'll come to that in a second. So this is the core that we made using this old tooling. So this face here is the face that was rammed up against this face, and you get a reasonably good finish on that because you're pushing sand up against a hard surface, and the finish is important for an impeller because the smoother it is, the better the impeller will perform. If we flip it over to the other side, now you see some of the problems. So the surface that was at the top that we had to strickle off, you're never going to get as good a smooth finish as you do from a ram surface. So already the quality isn't as good as a potential 3D printed alternative. And the second issue is, and if I can find it, you can see here, one of the core irons is just sticking out. Now that's happening on the edge, so it won't actually be in the casting, so that's not a big deal. But sometimes when you ram it up, you might find you have a bit of a core iron sticking out here or here. And the problem with that is that you end up with the core sometimes welding, the core iron welding itself to the casting once you've poured it. So you can imagine that trying to get the core irons out after you've poured the job is quite difficult and takes a lot of time. So if you could avoid using core irons, that'd be great. And the 3D printing allows us to do that. So let's switch to the future. This is the 3D printed equivalent of the same thing. As you can see, the surface finish is quite good all over. You get a uniform texture all the way around. You don't have to go through all of the problems that you go with this process, where after you've rammed that up, you've actually got to roll it over, take the core box off, and then very carefully you've got to remove all of these vanes to create these cavities in this older version. It's very hard to do that without actually breaking the core through here. The reason being that the sand that we're using is set over time, and the longer you leave it, the harder it gets. So there's a sweet spot. You've got to roll it over, and while it's still in a plastic state, very carefully wiggle that vane out without breaking the core. So you could probably make 4 or 5 cores this way an hour. It's very inefficient and takes an experienced core maker to do it. So I'd value that core at about $20 to $25, depending on the experience of the core maker. The ones that we got printed were $29, so they're slightly dearer, but the fact that you just click a button and you've got 210 of them, and then the person who would have spent weeks making these can now be molding and making money in the foundry in another way, that easily justifies the extra couple of bucks to go this way. So you can't print a model without, you can't print a core without a CAD model. So I thought I'd talk quickly about that. I'll just get Paul to hold the camera while I show you. So here's our CAD model of a impeller core. Quite often when you get these jobs, all that the customer has is the old tooling. They don't have any drawings, they don't have a CAD model. They might have a two-dimensional drawing. In this case, they did. So I'll just turn that on. So basically, I just import the two-dimensional drawing, and then as you can see there, I'm effectively tracing with the CAD model the shape of the impeller like that. So you can see the green line there. I might just turn the model off so you can see it. That's the drawing there, and we're basically just trying to draw over the top of it. So that gives us the shape of the impeller, but it doesn't give us the vane detail. So if we use another drawing for that, turn this one on. This is another photo that I took from above, and you can see the vanes. It's just a photo of the core box that I showed you before. So then effectively I'm tracing the path of the vanes and then creating a CAD model from that. And that's how you generate the CAD model. And then the only other thing you've got to do is check to make sure that you've got the core print and everything matching what your pattern actually does. So now that we've done that, we'll probably go into the shed and show you the unpacking process. So bear with us a sec as we wander out there. So here is the box, exactly as Gary sent it. And Paul's just going to crack it open now to demonstrate how you remove the cores. As you can see, the top, as Gary said, it's only 4mm thick, so it comes away really easily. And you can actually see the edges of the impellers inside. So the white sand you're seeing there is the loose, unbound sand, the sand that wasn't printed with binder by the printing head. And it's essential in this process because it's essentially our packaging. It's what's protecting the cores during transport. So it's convenient that it's there. We've unpacked 4 boxes of these already, and so far we haven't had a single broken core. So the process certainly works well in terms of protecting the core. Quick wiggle and you lift it out and just tip the sand away. See the vanes there, they've still got a bit of sand in them, so you just got to give them a bit of a hose down with some air, clean them out. Which we'll do now quickly. So the problem that Gary was talking about earlier is that he essentially does the same thing as this to check the core and then has to repackage it in sand. So the same thing's being done twice. It's just double handling. So there's a clean one there. It took us, I don't know, about 20 minutes to get them all out. It's not a big deal. Might just grab one more out and then go and show you how they work in the mold. And you might remember from the video before that Gary said he had some other little cores hidden inside this job box. They're just under the surface, sitting down in here, a few down the side. I'll show you one here. These were taken out of another box, and you can see that's the top of one of the cores there. As Gary mentioned, we do bake the cores just to remove any residual moisture. You don't want that moisture turning into gas, which can get into the casting. This is the pattern. So got the moulding machine there for those who haven't seen one before. And the sand comes down through the barrel of the moulding machine, gets mixed with your chemicals, which are up there in those IBCs. And once it comes out, you've got about 10 minutes before it goes hard. So you fill these two flasks up, and you might remember at the start of the presentation I talked about how you had two parts of the mould, the bottom half, the top half, and then the core that goes in the centre. So this is the cope, the top half. This is the drag, the bottom half. So we've got a couple that we prepared earlier over here. So there's the drag half of the mould there. And here are the cores that we've baked in the oven, ready to go. And as you can see, they are a really nice fit. It should be flush with the top of the mould, which it is. And it's just a matter of closing the mould and pouring it. And we've got one which we've done earlier, which we'll show you now. This is the pile of cores that we've got here, ready to go in the oven. We just heat them up for about half an hour at about 100 degrees Celsius. For this particular core, we find we get a good result. So I'll go and knock this one out. This is one that we poured earlier. As you can see, the metal goes down that hole, fills the cavity, the casting impeller. And we've got a little insulating sleeve here with a feed on it to make sure that the casting isn't porous in the centre. Also just going to quickly knock it out. The important thing I want to show here is how easy it is to get the core out from the casting, because previously this took a lot of time. Out for a sec, but I think we're back. So what we've just shown is the knocking out of the impeller. So this one here is one that we poured earlier. As you can see, the bronze has surrounded the core, and the core is sitting down inside here. So that was the 3D printed core, and the breakaway is really good. They come apart quite easily. And Paul's just going to give one a tap with a hammer so you can see how easily that the 3D printed core breaks down and falls out. All the sand pouring out. Normally the fettlers are over the other shed scratching away for ages trying to get them out. And remember as well that they're not only getting the sand out, they've got to dig those core irons out. And see the internal geometry there. We've got a bit of flashing across there, which we just cut away. And that's probably a good point to throw it back to you, Gary.
Thank you, Adam. Very informative, and it's really nice to see the melting together of the old and the new. This has been done often in other places where you have a 3D printed part, but you can insert it in conventional molding. The two work together very well. So I'm going to now talk about another case study, and this one relates to Germany. The screen should be up by now. Last year at GIFA in June, Voxeljet made an announcement of their new machine, which they're calling the VX1300X. It was developed as a joint project between Voxeljet, who did the machine, the printing side of the machine, Laura Mendi in Italy, who did all the automation, and ASK Chemicals, the binder system. I know it's a bit of a noisy slide. You can't see the detail. Don't worry, we're going to get up close. You'll see it all. This is a slide from Voxeljet. It's hard to read. Don't worry about trying to read it. I'll explain it. It's comparing conventional molding with a core shooter compared to what they call HAM, hybrid additive manufacturing. A lot like what Adam showed you, the hybrid between 3D printed and conventional molding to make a part. The big difference with this is mass production. In December 2018, Voxeljet and a premier German automotive manufacturer signed a framed contract for 5 machines. 2 of those are installed in the production plant at the moment, and they will be operational, I think, probably later half of this year, and then Voxeljet will get paid and another 3 machines will be delivered. All going well. let's talk a little bit about why they would want to do this. The top image there is the conventional core shooting. Automotive design engineers are trying to get every last little bit of efficiency out of engines. To do that, the complexity has increased over time. Remember I said complexity comes for free with the 3D printing? Well, they've made these water jacket cores, and the application is water jacket cores, so complex, conventional molding cannot make them in one part. So that top image there is basically showing that you make it in two parts and you join them together if you want to do core shooting. Whereas 3D printing can make it as one piece. That has advantages. You can all imagine if where you glued them together, the glue come apart and you've got an engine which doesn't have cooling in one area. That's the driver behind it. Now let's talk about the binder system. This machine runs on what they call an inorganic binder system. It's basically sodium silicate. So the silica sand in the printhead is the binder, which is sodium silicate with water and maybe some other pixie dust and some other things that ASK Chemicals developed. It then runs the same way as our VX1000, where the printhead puts the binder on. But there's a twist. This VX1300X machine runs 10 times faster than my machine here at CSIRO. The VX1300X takes 5 seconds for a layer. Mine takes 50 seconds. I take 22 hours to do a job box. If it could do a full job box, it would take 2.2 hours. Think back to those pie charts that I showed you about the cost, the printing time cost. You can substantially reduce that. Let's have a look at the machine itself. This is an animation that VoxelJet put together. It's going to open the lid. So how do they get 10 times faster? If you remember back to the video that I showed, our printhead was reasonably small and it indexed across the bed 8 or 9 times. This has only got one printhead, and the printhead is the full length of the box, and the length of the box is 1300 millimeters. On the left side and the right side of that printhead are recoaters and infrared lamps. So basically what happens is every sweep, like that sweep there, it's laying down sand and printing. Now, laying down sand, printing. Go back, lay down sand, print. So every movement, it's printing a layer. That's how they can be 10 times faster. The infrared lamps are to just dry a little bit, because basically what you're doing is printing a lot of water on that sand. It's quite wet, and we know what wet sand is like. And the reaction of the sodium silicate is not happening yet. So the infrared lamps dry it just a little bit, but not a lot. Now, what they don't show you is the next bit. Remember I said the label was a big component. Well, imagine trying to unpack these things. Well, people touching them with their hands are gone. So when the job is finished, the job box comes out and they have microwave top and bottom to heat and do the final drying and setting of the sodium silicate. It then moves down the line and the sand falls away through like a sieve underneath. Robots pick up the individual cores and blow them clean. They go down the line and they're assembled in the mold. I don't know if the robots assemble them in the mold. I know the automotive companies in Germany, particularly Volkswagen, they have robots that put the core in place. It has vision system, make sure it's in the right place. It also has tactile feedback as to whether it's getting resistance. I hope you can see this. This is what that machine is making, not this exact one, but these sorts of things. It's very complex and it's quite delicate. Another thing about that VX1300X is the depth that what they print is only 200mm max. They don't use the full 500 because they can't. It's like, imagine wet sand on wet sand on wet sand. It won't hold up. So they're just printing basically one layer of these cores, then it goes out of the machine, microwaved, hardened, unpacked, and into the molds. So what I wanted to say in my wrap up is some people think about 3D printing as prototyping, product development. It's not. It's production. That German case was mass production. In Australia, Adam has been very sort of progressive in his thinking and willing to try new things. He's replaced conventional molding with 3D printed cores, and he's looking at other applications as well. I've spoken to other people too about our printing in a box and how it substantially reduces the cost. So keep this in mind. Maybe you can think of an application in your foundry or your part of the industry. Give me a call. My contact details are there. If you want to hear it from the horse's mouth, sorry, Adam, you're not a horse, but call Adam. And just want to say thank you for listening. And I'm now going to hand over to Alan. And some of you, I hope, have been able to find the question and answer feature on the right of your screen, and maybe you've put in some questions. And Adam, Alan, have you got any questions?
Hi, Gary. Thank you. Thanks for that presentation. Everyone online, you'd be aware that by now, of course, that this conference call is a little different from Zoom. You can't just come in and speak. But what we've got is actually two systems running, and there's an IT bloke from Soro paddling hard to keep it all working for us. So if you have some questions, we very much want them. Please put them into the Q&A section you'll see on the right-hand side, and not in the chat section. And as I speak, we've got some questions coming in. So let's just go straight into them. The first question I've got here is from Adrian Camps in WA. And the question was asked, what software is used for the design? Now that was in relation to the impeller core itself. I'm not too sure if I can direct this question to Adam or Gary.
Adam.
Yeah, I'm happy to take that one. I was using SolidWorks. It doesn't really matter what CAD package you use, so long as you can draw solid geometry and preferably using a parametric modeling software, which SolidWorks is. You can print directly from STL, but an STL file is something that you've scanned and you've got a point cloud, and then you may have reassembled into an STL file. It's not as useful because you can't edit that geometry easily like you can with a parametric model. So I, generally speaking, start from scratch and reverse engineer from the drawings. But yeah, SolidWorks, AutoCAD, NX, Gary could probably list some others as well. But so long as you become proficient with one package, you'll find that you can do most of what you need to do. Back to you, Alan.
Thanks, Adam. I'll just add to that. He's correct. Use any package. If you want the job printed, I forgot to mention in the slides, you got to provide to me an STL format and talk to me beforehand, because you need to use a certain resolution to make sure you don't get facets on your print. Back to you, Alan.
Thanks, Gary. Adam. Right, the next question you got here is from our David Sykes down in Geelong. Howdy, David. Question on the design of the impellers. Can the design take advantage of core printing rather than a copy of the existing design? Yeah, again, to either Gary or Adam. I'm not too sure which one of you would like to take that. Is that question clear? I'll repeat it. Question on the design of the impellers. Can the design take advantage of core printing rather than a copy of the existing design?
Yes, yes, it can. I'm not a hydrodynamicist, so I don't know specifically the details of what a perfect impeller design would be. I think from the discussions I've had with the engineers at GARM, who was my customer, the idea is that it's as smooth as possible to finish inside the impeller. But thinking aerodynamically instead of hydrodynamically, I know things like golf balls where you've got dimples on the surface, so maybe for air applications or something else, you would be beneficial to print a different surface finish, which you're not limited to doing with 3D printing, but you certainly would be using the old-fashioned method which I showed you. So yeah, I don't know is the short answer, dynamically what it should look like, but yes, it would be quite easy to alter the surface to accommodate whatever design was required by the impeller. Back to you, Alan.
Okay, thanks, Adam. I haven't got any fresh questions there, but still please use that Q&A function and answer your questions. I do have some questions on my own. With that high volume voxel jet that you're showing us, Gary, was that video in real time, the movement of the head, which was each squeak doing a layer of sand?
Okay, that's an animation developed from CAD drawing. Whether it's real time, I'm not sure. I could run it again and time it. It's about 5 seconds per layer. I think it would have been close to real time. So yes, it's very fast, and this is it's a good point. All 3D printing manufacturers around the world are trying to make bigger machines that run faster and cost less, because basically the 3D printing market in the world, items produced by 3D printing, is growing at a compound annual growth rate of around 30%. I think everybody here in the foundry industry would love to see those sorts of numbers.
Is the growth in the high volume automotive area, or you're seeing, is the same sort of growth in the low to medium volume area as well?
Yeah, it's a good question. Predominantly the uptake of 3D printed objects, particularly metal and things like that, are in aerospace, defense, automotive, sporting, did I say medical? But so they're the ones which I guess are some higher value items, but not automotive. Automotive are very price sensitive. They would not have adopted a 3D printed core unless there was a good price incentive. So it's not only the price, it also gives them flexibility. So whether it's in the small to medium sized things or small volumes, not too sure, Alan, but as an industry wide, that's the growth.
Yeah, okay. I don't need to dominate the question time because I've got a flood of questions here for you. The question here from Chris Malone: what is the shelf life of a printed core?
I think I better answer that one. And I think, I can't remember where. It might have been the last time I gave a talk to AFI. It might have been the Queensland National Conference. And Mikhail Dernamcourt answered that. We printed some cores for them. And I think he kept it for a year. And it was still all right. But a word of caution, it's a furane-based binder system which degrades if exposed to UV light. So if you want to keep it for a long time, put it in a box and make sure it doesn't see any light. And you can keep it for a very long time. But not many people want to keep cores for a long time. But maybe if you print a whole box and there's 200 or 300 in there and that's your whole year's order and you want to just dribble them out, yes, you could keep them for a year, but keep them in the dark.
So I guess a twist on that question would be, is there a difference between a 3D printed core in a resin system versus a traditionally made core from the same resin system?
Yeah, there's a big difference. If you want to hear it from the horse's mouth again, give Gary Yates a call. He'll tell you what the big difference is. The big difference is that 3D printed molds and cores, remember it's a layer by layer process. The sand is just falls into shape, and it's just sort of like a grater blade made smooth. There's no compacting. Also, the sand is a very narrow size distribution. So when you put all this together, you end up with a core and a mold that's extremely permeable. It breathes. You can basically get the air gun on those cores that Adam had and blow from one side, and you'll see the sand blow off the other. It breathes. So venting and breathing is a big benefit. Gary Yates loves it.
Yeah, good. Just a comment here. When before Gary, you gave the example of the complex water jacket core being printed in Germany. A comment here from Phil Guilfoyle, Vintage Restoration Management, is relating to the water jacket cores on the 1914 Grand Prix Village. I hope I pronounced that correctly. Engine molds printed at Lab 22. They reduced from at least 36 very risky and difficult to assemble cores to 2 robust, easy to assemble halves. And it was a very successful application in replacing complex patterns in core boxes. So hybrid use of voxel jet cores is the right way to go. So that's a strong endorsement there from Phil Guilfoyle.
Maybe if I just comment on that, Phil is trained in the operation of the voxel jet, and if you want to see him, he could do a job for you. That was a great project, the 1914 Delage reproduction of the engine. And yes, it reinforces the complexity comes for free. You know, forget about draft, forget about undercuts and all those sorts of things. You've got a lot of degrees of freedom, and yeah, the new and the old go together very well.
I'll go now to a question from Ed Fitzgerald in WA. Adam, did you have to have any change in your core painting process?
For these particular cores, we actually didn't paint them. The traditionally made core, so this one we did paint, particularly because that back face wasn't a good finish because it was strickled rather than rammed. But we found that with the 3D printed core, the surface was generally good enough and uniform all over that we didn't need to paint them at all. So we didn't. And the customer actually, before we volume printed 210 of these to fill the order, I've got a couple done, and we cast them and had them machined, and they pressure tested the output on the impeller just to make sure that it was moving the right amount of water, and it performed comparably with the existing approach. So it was very handy to not have to paint them. It's just more consumables and more time saved. Back to you, Alan.
Could I just add a bit to that, Alan? Sorry, Ian, it's a good question. I just wanted to add a little bit. Remember that the core is very porous, so when you do put a coating, it might absorb a lot more into a 3D printed core than a conventionally molded core. So just keep that in mind.
Well, we did try to paint one just out of interest. In fact, we tried to immersion dip it, and normally, if you've had experience painting cores and then you set them on fire and let the spirit burn away, it only takes a few seconds for that to happen. With this particular core, because it is so porous, they stayed alight for a long time. So they do absorb quite a bit of spirit. So it's just something to be aware of. So if you can avoid having to do it at all, which the finish allowed us to, then yeah, just don't do it. Thanks, Alan.
And that goes to a follow-up question from Ian asking, did vents get printed in the cores? Yeah, do you like to comment on that?
I'll take that one. What we did initially was we printed 2 versions. This version doesn't have a vent, but the other one, we printed slots in here to let the gases come out, and then we drill a vent hole off through the cope of the mould to let the gas out that way. We thought we'd try both methods and see if it was necessary. For this particular core, because it's quite thick here, the bronze, or the temperature of the bronze, doesn't bake the hell out of it too badly, and we found that we didn't get any blowholes in the casting whether we vented them or not. So for the production run, we opted to leave the vents out only because it was just extra work to blow them out with the air gun. Different cores, however, this is another impeller I'll show you now. This one's only 4 millimeters thick, so it's a bit trickier. And the temperature of the bronze, you've still got the same section of impeller either side, and it really bakes the core quite hard, generating more gas. We're still trialing these, so I'm not sure how they're going to go yet. We've cast 2 so far without additional venting, and they appear to be okay, but until we machine them, we won't know for sure. But yeah, there is certainly provision for printing inside the core to help you get the gas out. That's one of the great advantages of this process. Like Gary said, you're not worried about undercuts or any other limitations that you have with a normal core making process. The only thing that I would mention that's worth bearing in mind is that if you print a blind hole, so if I go back to this other one, if you print a blind hole rather than a hole that goes in and then comes out in a loop, when you blast air in there, if you overdo it, the sand will come loose inside the hole and start eroding the hole away. So you really need a through hole that goes like a loop that goes like that. You can still do it, just so long as you're careful and you don't overdo it with the air gun, you'll be fine. But yeah, just be wary of that when you're doing pockets. I don't know if Gary has a comment to make on that. Gary?
Yeah, I do. It's a very good point. It's one of the big advantages of 3D printed cores. You can have very complicated venting paths. And I would recommend that when you vent to atmosphere. So you can print a path so you come out at some point back to atmosphere. Because remember, the core is very porous, so all the air in there, when it gets hot, it'll expand. And if it builds up pressure, it's going to go in your metal. So vent it to atmosphere. Okay, that's all.
Thanks, Gary and Adam. I've got 2 questions here that are similar. One from Adrian Camps in WA and another from Ewan O'Leary. Adrian's question was, can different sand systems be used? And in a similar vein from Ewan, can you print different sand types, so silica and chromite? Oh, actually, I should have read this a bit better. Can you print silica and chromite in the one core?
It's a good question and get asked this often. Think back to the process. It's layer by layer. So you would have to, if you want to print different sand types, you'd have to have one full layer of silica, then somehow do another layer of chromite or something else. I don't know of any machines that do that. So the short answer is no, we can't do that here. Can we do other sand systems besides silica? Yes, we can. Can I offer them to you tomorrow? No. But if there's enough interest out there, we have looked at Dynasand, which is like Cerabeads. It's an artificial sand. They basically melt it and then blow it, and it's all spheres and a tight size distribution. Long as the chemistry of the sand is compatible with the furane binder system, yes, we can do it. Chromite sand is a bugger because it's very angular, faceted. It doesn't flow very well. So another important part of the sand for 3D printing is it has to be not too angular, a little bit rounded, so it flows. I hope that answers your question.
Okay, and of course, for anyone who has been asking questions, if they feel they'd like more detail, you've got 2 options. Just add a follow-up question here now, or contact Gary and Adam at a later point. I don't have any further questions in the queue, but I did want to ask a little bit more around, well, Adam, I'll start with. You've used this for the impeller. I don't know if you can say, but is there other, and this is a thin, you've had good reasons to go to 3D printing for the impeller. Thin core, difficult to make manually. and some other advantages with the 3D printing. Is there others in the product range that you produce that lend itself to 3D printing, do you think? You may or may not be able to answer that.
No, there is. At the moment, it's all about the impellers because there's actually, I'm going to guess, about 10 different types that we make, each with a different core. Some of them actually share a core, but they have different vanes. So that's actually really easy to facilitate because it's a small change to the CAD model, just to change the vane geometry so that you can use the same core for a different impeller. I've got other examples of cores for the casting that we make for United Rail. It's a trip valve body. I've got some of the tooling here. It's a bit hard to explain, but I'll give you the quick version anyway. This is a jig that the core sits in. So you make one core and it sits in the jig, and then there's another core that gets glued onto the top half of that core. Then we make those in the sodium silicate process with cold box. Then we blow 2 other cores on the hot box core shooter, and then we glue those 2 cores around this core assembly. So the core's now 4 pieces. And because you've got parting line joins on all of the 2 halves, we have to use the mold paint, the ceramic or the zircon mold paint, and bog all the joins up because this is all inside the casting, so you can't feather it and dress it, and we want it to be nice and smooth. So I'll guess it probably takes us 15 minutes per core assembly by the time you make the 2 halves, blow the other 2 pieces, put them all together, glue it, put the mold paint on, and then flash it off and then place it in the job. It's a really good candidate for 3D printing because you don't print it as an assembly, you just print it as one solid core without the limitations of drawbacks and whatnot. That's just one example, but yeah, pretty much every new job that we get here, I look at objectively and think, well, is there any way that we could use a 3D printer to reduce the labour cost on it? But that's just one example. Thanks, Alan.
And then another question in relation to the packing sand that came with the cores, that loose unbonded sand, was that something that you needed to send back to CSIRO because it's a valuable commodity, or not? This ends up with the rest of your sand system.
Maybe I could answer that. I didn't go into that component of the costing, but the activated sand is not that valuable. Our system was originally set up that the unbound sand that was clean, we would put in a used sand silo, and we would mix 2/3 new sand, 1/3 used sand. We've stopped doing that because basically the effectiveness of the activated sand with the acid activator drops off with time, particularly as the sand particles rub against themselves in transfer systems. So the quality of the print is never as good. So we've stopped doing that. I don't put any value on that. That loose sand and the printed sand can be sent to a thermal recycler. They heat it up to 980 degrees, burns the binder off, and then the sand can be reused.
And that is happening or not happening elsewhere in Australia?
All of my sand and printed sand and unbound sand goes to Macpro Sands. If you talk to Rob Delavia, he's got a deal for you.
Yeah. And a general question for Adam. Adam, what would go into your decision making about whether you would go to the cost of purchasing your own printers rather than purchasing a product from CSIRO?
Initially, exactly the cost of the machine. Gary could probably give you a better indication as to what these machines cost, but Gary, I'm sure, will correct me. But I think that one in particular was about $1 million, which is beyond my price range, but certainly feasible to hire in this sense, particularly when you do it the way that we've done it with the boxes being printed around it so that you reduce that labour cost. But yeah, at the meantime, I suppose it'll be like all 3D printing technologies. Initially, only a few people have them, and you lease that service effectively. And then over time, as it becomes more popular and more affordable, we'll see a transition to maybe foundries having these in-house. Gary, do you have anything to add to that?
Yeah, just quickly. So the machine was $1.1 million. They're not cheap. It's the only one in Australia. So if you want 3D printed sand stuff, come to CSIRO. Our labour charge out rates are reasonably high. There are alternatives, Phil Guilfoyle, Shane Corish, and some others. So you can use them as a service. The charge out rate will be the same, $70 per hour for the machine and $2 for the printed sand, and whatever labour rate that they put on it. The $70 per hour for the machine is quite a good rate because we've written it off already on the books. And that price is basically enough to maintain the machine. So the machine's not used every day, and there might be 20 to 40% utilization. Not all of that's commercial work. So we get enough money to maintain it. You know, the print head's got to be replaced every 3 years or whatever. So you don't necessarily have to have your own machine. You've got one. It's in Lab 22. And you can promote your business as being able to provide 3D printed cores or molds. Maybe at another time I'll talk about this, but Lab 22 is transitioning more to a research model than a commercial model. And I've been asked to consider a transition of that voxeljet machine into industry. In speak, that means sell it. Somebody in Australia buys it, or some people in Australia buy it, and it continues to be of value to the industry. More about that another time.
Mm-hmm. Yeah, chapter 2. Okay, I could keep on asking questions, but I don't want to keep to bore people. If there's no other questions from the audience, we'll I'll give it a going. I'll now pass over to our AFI Vic President Amber Maxwell. He'll do a wrap up. Over to you, Amber.
Thanks, Alan. Appreciate that. And thanks for coordinating our question and answer session. Again, a huge thank you to Gary and Adam for sharing your experiences and these case studies with us tonight. I'm sure there's a number of people sitting in front of their screens right now contemplating opportunities within their own businesses where this technology could be applied, and thinking about the benefits that they too can achieve as a result. Just before we wrap up, I just wanted to give you a quick update on the AFI Vic program. In June, we have a presentation scheduled to be given to us by Dr. Roger Lumley. It's currently scheduled for Wednesday, the 10th of June at the Village Green in Melbourne. COVID restrictions, of course, may have an impact on whether this goes ahead or in what format we do present this. So please keep an eye out for an updated email in the next week or so, where we can give you some further information on if that's going ahead, how it's going ahead, and we'd love you to join us if you're available. Finally, the conference, October, it's fast coming up. We are continuing to plan for the conference, the 55th AFI Annual National Conference, to be held in Christchurch. We'll be sure to keep you updated. We hope everyone has received a little update letter. I think it was about a week and a half ago. Hopefully everyone's got that. If you haven't, please let us know, and I'll be sure to get you on the mailing list. We'll keep you updated with our progress as this evolves, and we look forward to seeing you all there when that happens. For now, stay well, stay safe, stay healthy, and we'll see you soon.